So now we're going to look at a couple of the classic free radical reactions. And the first one is called free radical halogenation. And the idea here is this is important because this is one of the few reactions that we can actually perform on an alkane. So there's not a lot of reactivity in alkane. Remember, we define that as not really having a functional group because it's very hard to get alkanes to do something. With this, we can get an alkane to add a halogen on it, but we need to use free radical chemistry. So free radical halogenation follows a radical mechanism, so we're going to look at that. And so with this, we're going to be using, for our radical source, a halogen, and then we're going to be using UV light. And so you've probably heard about this. UV light is, or the high-powered version of UV light is really bad for us, and it can cause burns. Now you know why, because UV light tends to hit bonds, and it has so much energy, it can cause bonds to undergo homolytic cleavage. Homolytic cleavage means you're forming free radicals, and then free radicals start reacting with things and damaging stuff, and that's what causes the burns, is from UV light. So here we're going to be using UV light, and it's literally like you sound. You have a little chamber, there's a bunch of ultraviolet lights inside of there, and you lower your reaction tube inside of there. When we look at this, it's very simple. It's a type of substitution. We kick out one hydrogen and then we replace it with one of whatever our halogen we're playing around with. So, this could be chlorine or bromine, things like that. So typically we stick to chlorine and bromine. But what we really need to do is look at one of these mechanisms of a free radical reaction. This is one of the other places where free radicals are different than the other chemistry that we talk about. So when we talked about mechanisms beforehand, they were very linear. You said step 1, step 2, step 3, and at the end of step 3, you made your product, and that was it. Free radicals don't really work like that. There is multiple mechanistic steps that are kind of all happening at the same time. So I like to refer to a free radical mechanism as like a bunch of wheels, and they're all spinning at the same time. They're doing different things, and then your product kind of pops out in a couple of different places. So it's not linear. You don't go step 1, step 2, step 3. Here there are multiple steps, and they are kind of all occurring at the same time, and as part of that you make your product. So let's take a look at this. So with all free radical reactions that I know of, the first step is you got to create free radicals. They got to come from somewhere. And so this first step is called initiation. So there's 3 main steps in our free radical halogenation. The first step is called initiation. And with this, we are creating free radicals. And by initiation, we're taking something with no free radicals and turning it into something with free radicals. So here it is our chlorine. This chlorine bond is relatively weak, such that if we hit it with some UV light, this will undergo homolytic cleavage, 1 electron going to each chlorine, and we end up forming 2 chlorine free radicals. Okay, so this is the beginning. This reaction won't occur until I start making these chlorine free radicals. Now the chlorine free radicals go on and continue the reaction. So we go on to step 2, which is called propagation. And by propagation, it means, we're propagating the free radical. And with these reactions, there are, what we're going to be doing is putting in a free radical and getting a different free radical out. So that's what we mean. It's spreading from one thing to another. So in here, and this is what's nice, for each major reaction or mechanism step, there's kind of multiple steps that can be involved. So for the first step, there's one sort of sub-mechanism inside of here. For the second step, propagation, there's 2 sub-mechanisms here. There's 2 ways that we can undergo propagation in a free radical mechanism. So the first thing is we have our free radical, so we've created this. This free radical can do an abstraction from our alkyl group. So remember, abstraction means it's just going to grab onto a hydrogen. So it's removing this hydrogen, it's going to grab onto it. This electron, this bond is broke. 1 electron's going on to the carbon, 1 electron's going into the forming the ClH bond. Here my free radical is going into the ClH bond. So overall, the hydrogen moves to the chlorine, and it is removed from the carbon, and the carbon gains a free radical here. So that's what we mean by propagation. We've put in a chlorine free radical, and now we get a methyl radical out. So now that we have a methyl radical, the methyl radical can propagate by reacting with one of our chlorines. So we still have plenty of the chlorine bond inside of there. And so this methyl radical is going to undergo a type of abstraction. It's going to grab onto one of these chlorines and pitch out the other chlorine as a free radical. So this is still a propagation. We're putting a free radical in, we're getting a free radical out. And so this is a type of abstraction. So we break this bond. One electron is going to the chlorine, so we form a chlorine free radical. The other electron is going with the electron from the carbon free radical. So these two electrons are coming in to form a bond, and that's where we form the Cl bond. So here, notice this is our product. So this is the product that we want. And we're going to see that it kind of pops out in different places. Notice we're not at the end yet of this reaction, but during this step, this is one of the ways that our product can be made. So that's the idea, is there's a lot of different things going on, and they're all happening at the same time. And here, this is one of the ways that we can create our product during this overall mechanism. So we had step 1, step 2 is propagation, step 3 is termination. So the idea is I can't really stop this reaction until I get rid of all the free radicals. So termination is the end. So we when we turn off the UV light and we have radicals want to react with something. So when they're done, all the free radicals need to go away. So when I say termination, it means we're getting rid of the free radicals. It means we're putting free radicals in and getting no free radicals out, or molecules with no free radicals out. So same thing, this is the third mechanistic step. There are 3 sub-reactions inside of here. And really how we get rid of free radicals is coupling. That's one of the main ways that free radicals kind of destroy themselves, is by coupling with another free radical. So here, if you look back, we have 2 main free radicals in our solution. So we've created these using the first 2 mechanistic steps. We have the methyl radical or alkyl radical here, and then we have a chlorine radical. And the idea is we're going to look at the 3 different ways that we can combine these 2 free radicals together to couple them and get rid of the free radicals. So here we have the chlorine free radical, we have the alkyl or the methyl free radical. Both can put 1 electron into forming a bond, and we end up forming a carbon Cl bond. And so notice here, this is our product. And once again, this is one of the ways that we can make our product during this reaction, is through the termination step. The other 2 are kind of inconsequential. The other thing, I can take 2 chlorines and kind of do the same thing. I could do a coupling. And when we do that, we're just going to form Cl2 again, our chlorine that we started our whole reaction with. And then one important side idea here is it's capable for 2 methyl radicals to come together and couple to form this species. And so this is actually a side product. This is not the product that we want. The product that we want is the alkyl substitute here. This is the product that we want. This is something that we don't want. And it's called a side product. When we draw out the products of these reactions, later on we will discount it. We will say that it's not the major product, so we won't worry about it. But this is one of the things you want to consider, because this is something that's going to be created inside of your reaction, and it's something you're going to have to purify out. So one of the things I was told, and this is a good way to remember this, is it's very hard to control free radicals. Free radicals kind of do whatever they want, and it's really hard for them to come out in a very linear process where you get like a really high yield of something, because they're so reactive, they end up doing reactions that you kind of don't want. So I mean, I'm sure there's some that work really good, but here this is the idea. This is an unintended side product where the 2 alkyl groups, or the alkyl radicals, couple together to form this species. So once again, it's a side product, it's part of the mechanism, but when we draw the reaction, we're not going to consider it. So let's look at a couple of products. So that's the mechanism of free radical halogenation. Here, one of the things you need to consider is that there's a lot of different hydrogens on a molecule. And there are ways of predicting kind of where will the halogen go on there, and it has to do with the stability of the free radicals that you produce and how many hydrogens do you have to leave. And so there's a calculation in there. I'm not going to worry about that, but I want you to know when you do a free radical halogenation that there's two distinctly different sets of hydrogens inside of here. So we have these CH3 groups. These are symmetrical, which means they're kind of the same. But then we have these CH2 groups here in the middle, and these are distinctly different. So the center carbon is different than these outer carbons here. And so I have the ability to remove a hydrogen and put a chlorine here to make this product, or I could remove a hydrogen and put a chlorine here to make, or let's say over here, remove one of these hydrogens and put a chlorine there to make this product. So the rule is I can make a product for each type of unique type of hydrogen that we have inside of a molecule. And you can kind of control it, but you end up making a mixture of these two. Well, how much of one or the other? There's actually a method for calculating the percentages, but you're really going to make both of them. It's kind of hard to just get 100% one and 0 the other. So for you guys, if I give you this, I want you to indicate that there are two different ways I can put a chlorine onto this molecule. This, once again, is overruled when we have a benzylic or allylic hydrogen or carbon inside of the molecule that we're doing this reaction on. Because when we form a free radical on a benzylic or allylic position, it's the most stable. So that's where the reaction is going to occur. So when we start this reaction and we start creating free radicals, and the free radical says, well, where am I going to remove a hydrogen from? It's going to remove it from the carbon that is benzylic or allylic, because that's where you're going to form the most stable free radical. So even though we have 1, 2, 3 distinctly different types of hydrogens inside of this molecule, if I do a free radical halogenation, the halogen will overwhelmingly prefer to go on the in this case benzylic carbon here. So the carbon that's directly attached to my benzene ring, it's going to substitute one of those hydrogens with whatever halogen we're playing around with. So we go from CH2 to CH with a chlorine, and so it dominates that because of the stability. So much so that I'm sure you make some amount, but we can definitely say that this is most likely going to be our predominant product because that position is so stabilized. If we look at another example here, I react bromine with this molecule, and this is one of those things, I kind of mentioned this before, that as you go along as a chemist, there's certain combinations of bonds and things like that just kind of jump out at you, and one of them is whenever I look at a molecule, I kind of see these allylic and benzylic positions because I know they're different than the other positions here. They get conjugation, so they're special, and we're going to spend a lot of time talking about that in 335B. So when I do this reaction, remember the reagent tells me what's going on. So I've got a bromine, I have light, and so this one's a little bit tricky. It's very easy to look at this and say, oh, I'm going to do something to this double bond. No, or not. So this is not a reaction for the double bond. It's a reaction for the alkanes. And so now that I think about it, this is a very common mistake when you have the reagents for a free radical halogenation. So Br2 and UV light, it's not going to react with the double bond. Actually, what it's going to do is react with the allylic position here because we form a more stable free radical. So there's some, remember, there's implied hydrogens coming off of here, and I know where this halogen's going to go. It's going to preferably go on the allylic position. So we have a couple other positions over here. It's not going to go there because it doesn't have that specialized conjugation. So during this reaction, I know that my incoming halogen is going to go on the allylic position like this here. So that just remember that when you see a halogen Br2 or Cl2 along with light or UV light, it's not a reaction with the double bond. It's actually a reaction with the alkanes or the CHs that are adjacent to it. So it's a very common mistake. And this is where it gets a little tricky. Is we're going to do use a halogen again here in just a second, but it's going to be slightly different. So we're going to fix it to do a free radical reaction with an alkene. So it's important to keep those separate. Okay, so the last reaction, and you can kind of see what I'm talking about. We're going to add HBr to a double bond, and we've already talked about that if we have an alkene, we can add HBr to a double bond, and it's going to follow Markovnikov's rule. So we talked about the mechanism and all that, and Markovnikov's rule says that our incoming nucleophile or species of interest goes on the more substituted carbon in our double bond. And so we already know how to do that. I just add HBr, break the double bond, form two single bonds, hydrogen goes here, bromine goes here. And this addition follows Markovnikov's rule. And the reason why it follows Markovnikov's rule is because it follows heterolytic cleavage. So you form a carbocation, an electron moves into pairs. And the idea is, what if I want to add HBr to a double bond and have it go anti-Markovnikov? And the idea is I can do that, but I need to involve peroxides. And the peroxides are going to change the mechanism. We're going to go from a heterolytic kind of mechanism where we had the carbocation. We saw that with straight addition of HBr. We're now going to go to a peroxide mechanism. And in doing that, that's going to put the bromine on the less substituted carbon, or gives us an anti-Markovnikov addition of bromine to our double bond. So we're going to do this, and it's exactly the same reaction. It's still HBr, double bond, but now we have put in some source of free radicals. And remember, there's a couple of different ways you can do this, but typically it's just peroxides, and I probably should have put the word heat underneath here, but the idea is the presence of free radicals changes the mechanism of the addition of HBr to the double bond, and that in turn changes our product. So here now I still break the double bond, form two single bonds, but now it's anti-Markovnikov. So our incoming, it's not a nucleophile so much, it's our incoming species of interest is going to the less substituted carbon. So here the bromine goes on this carbon, which becomes this one, and then the hydrogen goes on the other side and goes here. And so this is only because we have put in a free radical initiator. The free radicals cause the mechanism to be different, and then that causes our product to be a little bit different. So let's look at the mechanism, and it's kind of the same deal. It's going to go in a kind of a nonlinear sense, but the idea is the first thing I got to do is make free radicals. So in this mechanism, so we're talking about the mechanism of adding HBr to a double bond using free radicals. We do an initiation, so we see a peroxide, we heat it up, this peroxide bond undergoes homolytic cleavage, and we end up forming two oxygen radicals. Then we go to propagation, so it's still the same thing. And in this case, we kind of abbreviate the mechanism, so we're not going to show all the different variations. So we traditionally show all the kind of crazy variations in the free radical halogenation. But after that, typically we tend to focus on just the reactions that are important to us. So here, the next step after I form my oxygen free radical is we still undergo a propagation, but the propagation goes to HBr. So the oxygen free radical undergoes an abstraction with the hydrogen. So it pulls the hydrogen off, and it gains it, and it removes it from the bromine. These two, this electron, so the bond represents two electrons. One electron goes to the bromine. That forms a free radical. The other electron combines with the electron from the free radical to form an electron pair, or this bond. So we put in a free radical oxygen, and now we've gotten a free radical bromine out. So then the bromine can actually add to our alkenes. So we saw that before, that free radicals can add to a double bond, and so that's exactly what it does. And when we do this, the double bond breaks, one electron jumps onto this carbon to form a carbon radical. The other electron combines with the electron from the free radical, and that forms an electron pair, which is this bond between the carbon and the bromine. And the idea is, and I think did I mention it? Yeah. So here, it's the exact opposite. So we want to put our free radical on the more substituted carbon here. So because we're reacting with the bromine first, we get this Markovnikov addition, because by adding my bromine, anti-Markovnikov, by adding my bromine to the less substituted carbon, that puts my free radical on the more substituted carbon. So remember, free radicals are electron deficient. They want to gain electrons or stability from adjacent sigma bonds. So they want to gain stability. So they want alkyl groups. The more alkyl groups you put on there, the more stable the free radical. So the bromine is going to add such that the free radical that goes into the double bond, the free radical is going to go on the more substituted carbon. And so my bromine is going to go on the less substituted carbon. This is why the HBr addition to an alkene using free radicals is anti-Markovnikov. So now you can see we're almost to our product here. All we got to do is get rid of this free radical. And in this case, how we show this is by propagation to HBr. So there are termination steps inside of here. They kind of shorten this down just to make things a little bit more clear. But there's a lot more reactions going on than what we're seeing here. But in terms of making our product, all we have to do is put a hydrogen on this carbon and we will be done. So what ends up happening is the free radical does an abstraction from HBr. Once again, there's these two electrons, one jumps onto the bromine, so we end up forming a bromine free radical, which can go back and continue the reaction. One electron from the bond goes in and pairs with the electron from the free radical to form a CH bond. And so in the end here, we form our product. So if we look at an actual example of this, and there's a couple different ways I can represent peroxides. Sometimes they just write the word peroxide. Sometimes they'll draw in like ROOR, things like that. But same thing. Remember, if I just have HBr by itself, I get one product. If I have HBr with peroxides, I get a different product. Overall, it's still the same idea that we had with alkenes. I break the double bond. I form two single bonds. What goes on that single bond is an H and a Br, and then you say, where does the Br go? Is it Markovnikov or anti-Markovnikov? Here the bromine is anti-Markovnikov. It's going to go on the less substituted carbon. And when I look at this, I count alkyl groups. So the carbon on the left has one alkyl group. The carbon on the right has no alkyl groups. More substituted carbon, less substituted carbon. And so my incoming bromine is going to go onto this carbon. So I break the double bond, form two single bonds. This carbon is this carbon. It gains a hydrogen, so we go from CH to CH2. And then this carbon gains a bromine. So we go from CH2 to CH2 with a bromine. So the bromine goes on the less substituted or anti-Markovnikov.